So it's nice to know what area you're working in. Right. Silly o'clock in the morning. I was hoping the walls are soundproof. Just seen a guy on YouTube saying inverse square law suggests gravity ain't working right, basically. And he quite correctly said that inverse square law, as applied to light, sound, gravity, and all kinds of other stuff, says that the intensity of something, the amount of light that's hitting you from a light bulb, the number of radioactive beta particles hitting you from a beta radiation source per second, the intensity of sound, and the strength of gravity are inversely proportional. So in the case of the strength of gravity, it's a force. Inversely proportional to the square of the distance. So that's a special case, that's 0. From that there to here, whatever force you've got here at 1 unit of distance, call it 1. At 2 units of distance, it'll be a quarter as intense. At 3 units of distance, 1/9. 4 1/16. And he's quite correct about that. And what he says is that means the strength of gravity pulling you down ought to get smaller and smaller as you get further and further from the Earth. That's true enough. But he was talking about 1 mile or 2 miles above the surface. Now for a start, who the heck measures altitude in miles? Thousands of feet? Yeah. Kilometers or meters? Yeah. Miles? Funny choice of unit. Right. The problem with that is that 1 mile above the surface is there, and 2 miles above the surface is there. Because you're talking about distance from the centre of mass. So the surface is at the equator. Plus 1 mile be that, plus 2 miles there. So the actual change in distance is only that much. And I'm not about to do long division with those numbers on this piece of paper. I'm going to use the calculator. Right. That difference is new glasses. You are that many times further away, which means the strength of gravity that much further away change in the strength of gravity is, well, the actual strength of gravity is relative to what it was there. Gravity should be that many times as strong 2 miles up as it was 1 mile up. So you can measure that, but only with really, really, really sensitive instruments. You're not going to suddenly be able to lift cars just because you're up a hill. Right. There was another thing you brought up, which is terminal velocity. I need a fresh sheet of paper. When you do the really simplistic maths, GCSE, A-level, you tend to treat stuff as a point mass. Remember this? Aircraft are not dots. With a velocity and a force acting on it. And that's a single force, you've got a single acceleration, its velocity is just going to increase. And if you start off with an object travelling in a direction other than in line with the force, its velocity is going to increase in the direction of the force. So it's going to level out, start going downwards, faster and faster, while still going this way at constant speed. But that's a point mass aircraft over a flat stationary Earth, or a particle over an infinite plane of uniform density with no air resistance. Now, with no air resistance works if you're talking about geostationary satellites. That's easy enough, because there is so little gas out there that the air resistance is negligible over the course of 20 years. If you're falling through Earth's atmosphere, air resistance is a thing. Stick your hand out of the window of a fast-moving car and see for yourself. And on a falling object, air resistance is, of course, opposite to its direction of travel. On an object on a trajectory where it started off going upwards, air resistance will be backwards in its changing direction of travel. Air resistance increases with the square of the velocity, approximately. That means the faster you're going, the more air resistance you have. On an object in free fall, if it's just stationary, it has weight and no air resistance. So its net force is its weight, and that's its acceleration. As it gets moving faster, it has air resistance, so the net force is its weight minus that air resistance, and it accelerates less. Get it going faster still. And it has the same weight, or as it's fallen, it has, what was that number, 0.00001% more weight? More air resistance. There comes a point where those two forces cancel out, and that is terminal velocity. If the forces exactly cancel each other, there's no net force, there's no more acceleration. So where in the free fall, unrestricted, no air resistance model, your graph of velocity over time looks like that. With air resistance, it's going to do that and level out. Terminal velocity. as most of air resistance is due to how much air you displace, friction does play a part. The shape of your arse plays a part because a lumpy arse generates turbulence, and a really pointy arse allows smooth flow. That's why planes have pointy arses. For any standard shape though, a ball or a mouse or a human or a brick, actually a brick in free fall is really awkward because it tumbles and how much air resistance it has changes and it gets complicated. But if it's falling that way, that area is the amount of air it has to displace to fall. And air resistance at any given speed is pretty much proportional to that area. So if you have a scaled down version of that brick, it's absolutely identical in all respects except it's exactly half the size in each direction. It has a quarter the surface area and an eighth the mass. So 1/8 the force down, 1/4 the force up. I didn't measure the arrows, just pretend that's a quarter as long as that. This one has a lot more down force than up force, and this one they're balanced, so that has already reached terminal velocity. This is still accelerating. And you can simplify that to be the length cubed down and the length squared resisting it, assuming all dimensions are proportional to the length. Which means your terminal velocity it means your net force down is proportional to your length. But with air resistance being proportional to the square of the velocity, as you scale down, your terminal velocity, not television or transvestite, context is important, will be proportional to the square root of your length. Which is why, according to a man who did his research in Africa, back when human rights and animal rights weren't really a thing and diamonds were very important, dropped down a mine shaft, a mouse is scared, a cat is injured, a dog is killed, a human is shattered, and a horse splashes.